Okay, so today we are talking about Wi-Fi 101. We're going to go through the history of Wi-Fi a little bit, talk about some of the technical details in Wi-Fi and why it causes you problems and why sometimes it actually helps you out. Talk a little bit about Wi-Fi 6, and then we'll be set to go. So we'll start off with just a quick brief introduction on Zyxel for those of you that might be new. It's a single slide. Basically, we've been around since 1989 making computer networking equipment. Our US headquarters is based out of Anaheim, California. That's where I work. It's where our sales team works out of. That's our marketing department. That is our warehouse. It's also our tech support. So when you call in for help, you're talking to somebody that works at the Anaheim office, or at least did before the COVID hit. We've got over 100 million devices deployed out in the field, and we have offices in just about every major market across the globe. So now on to why you're here, Wi-Fi 101. So we'll start off talking a little bit here about some of the different players in this space. So you've got the IEEE. They're the ones who actually create these standards. Hold on, let me take a pause here. I'm getting a message. Maybe they're telling me there's something wrong with today's webinar. No. Okay. So the IEEE, they're the ones who actually create the standards. That's where we get 802.11 A, B, G, whatever from. Those are the numbers that they assign to those standards. If you look at Ethernet ports and things like that on the data sheets, you'll see also various different 802 rules put in place or standards that people follow. That all comes from the IEEE group. There is the Wi-Fi Alliance. So the Wi-Fi Alliance is a group primarily of manufacturers looking to help market Wi-Fi. So that's where the term Wi-Fi comes from. It's a little bit more friendly than IEEE. And they do product compatibility. Basically, despite the standards that are out there, someone needs to be around to enforce that everyone's following those standards. And even after the years these spend trying to ratify these new standards, there's still some things that are open to interpretation. So the Wi-Fi Alliance steps in and helps try to smooth those out and make sure everybody's creating products that can talk to everybody else. And then we've got the good old FCC. So the FCC decides what channels we can use, how we behave on those channels, how much power we can use, and things like that. So we use radio waves. So using Wi-Fi is very much like using those little analog walkie-talkies you used as a kid to talk to each other. It uses radio waves. So generally, as frequencies go up, it's easier to force more data onto the frequency, onto those frequencies, so it takes less time to send the same amount of data as the frequency goes up. But on the other hand, as frequency goes up, the signal is much more easily blocked or absorbed by obstructions. So the example I like to use in this presentation is cordless phones. Maybe some of the younger people on this won't help, but for those of us that are a little bit older, we'll remember cordless phones. Back in the day, we had these 900 megahertz cordless phones. They had these little metal antennas you pulled out when you got on a call, and they were fantastic, right? You could walk down the block over to your friend's house and still maintain a phone call. So unfortunately, there's not a lot of 900 megahertz space available. And again, it's a lower frequency, so the signal's traveling far, but you can't cram a lot of data on there. So there were complaints about sound quality. So the big next jump after that was moving cordless phones to 2.4 gigahertz. So it opened up more spectrum, so you could have more users on the phone at the same time without interfering with each other. Really important in condos and apartment complexes and things like that. The sound quality improved, but the range dropped off. So now you can no longer walk across the street to your friend's house on the phone, but you could probably go out to the backyard or the front yard and still maintain your phone call. So after that then came out 5 gigahertz cordless phones. And same thing, sound quality improved, range got less. So now maybe not only could you not go out to your yard, but maybe some corners of your house, you can't use that cordless phone without some sort of repeater. And you may notice that those frequencies are basically the same frequencies, at least two of them are, that we're using here for Wi-Fi. 2.4 gigahertz spectrum and the 5 gigahertz spectrum. So generally, to operate something that transmits radio waves, you have to get a license by the FCC. So the FCC has cut out these little chunks of spectrum, which everyone can use without needing a license. So 900 megahertz spectrum, 2.4, and 5. So these were all used by cordless phones over the years. And these days, Wi-Fi uses these bottom two, 2.4 and 5 gigahertz. So when we're talking about power, the most common thing you hear people talk about is milliwatts, right? 200 milliwatt, 500 milliwatt, things like that. But if you look at data sheets for business class products, you will normally not see milliwatts being used. Instead, you will see dBm. So both dBm and milliwatts are ways to measure the transmitted output power. dBm is a little bit more scientific. It works really well because you can add your antenna gain and subtract your losses from cables and connectors and stuff and get one number really easily. So power output's measured in dBm, increases to your through your antenna boosting, losses caused by cable runs and things like that are measured in dBi. dBm and dBi can be added together to get your total output power. So it's really convenient if you're trying to calculate link budgets and things like that. So generally, as for every 3 dBm of power increase you get, you're doubling the power as measured in milliwatts, right? So 20 dBm gets you 100 milliwatts output power. 23 dBm gets you 200 milliwatts output power. So this is an area where it causes some confusion to people, because people will go, well, I upgraded from 100 milliwatt to a 200 milliwatt router, I should get double the range. And the answer to that is no, you're not going to get double the range. We'll get to it here on another slide where we've got the formula for calculating how far your Wi-Fi signal is going to go. But power basically drops off as, I believe, an inverse square of distance. So, dBm is actually probably a much better guide or estimate of how much sort of increase you should expect to see rather than using milliwatts, which seems to kind of exaggerate it. So one of the things that people tend to overlook a lot is the signal to noise ratio. So the signal to noise ratio is basically the strength of what it is you want to hear versus the strength of other RF noise that might be going on. It could be other devices that are also using that same spectrum, the same channel you're using. It could be RF interference put out by other appliances in your home, industrial devices in your business, et cetera, et cetera. So this signal to noise ratio is really what determines how fast of a connection you've got and how reliable of a connection you've got. So that's really something you want to take a look at when you're troubleshooting issues with Wi-Fi signals, is you're not just looking at the signal strength, but you want to look at the signal to noise ratio. Another term you'll see a lot if you're doing some reading here is attenuation. So attenuation just means how much the signal is degrading as it passes through other mediums. So as the signal passes through the air, it degrades at one rate. If it has to pass through a wall, it degrades at a different rate. If it has to pass through a human, it declines at a different rate, right? So generally when it comes to Wi-Fi, the more water that's in the obstruction, the more that's going to get absorbed, and then metal will act as either to reflect the signal or in some cases can absorb and then retransmit the signal. So up here at the top, this is your signal here, or your formula here for calculating your distance. So this is how far you're going to get. So it's what, 20 log 10 of distance by 20 log 10 of frequency plus 92.45. So that's the formula you need to use to calculate how far your Wi-Fi signal is going to go. So just some short things here, some common obstructions. A standard window can give you a 3 dB loss. A tinted window, so something that's got some sort of metallic treatment on it to keep out UV, to keep out heat, can get you up to an 8 dB loss. A standard wall can get you up to a 10 dB loss. Really thick walls can get you up to a 25 dB loss, et cetera, et cetera. So the next thing I want to talk about here, which is really important, is that Wi-Fi is two-way communication. So think of this as like trying to hold a conversation with somebody, right? If they've got laryngitis, they can't speak loud, you have to move closer to them. Even though they can hear you fine, you have to get closer to them so you can hear what they say back. So even if you're doing something like streaming a video on Netflix, you go, well, that's only one direction, right? It's only from the AP to the client device. But it's not, because of the way Wi-Fi works, because of the way a lot of network protocols work. This guy here has to be able to respond back to the access point and say, hey, I got the data, it was okay, or no, hey, I got the data, Part of it was missing, please send it again. So there's a constant two-way communication going on. And what you find is there's a huge difference in the output power of your access point versus a lot of your client devices. So for instance here, you know, an access point is easily, a business AP is easily 500 milliwatts. That can be up to a watt of power. But something like your little iPhone is only putting out something like 25 milliwatts. So a huge disparity in the signal strength between the two. So what that means is this can shoot its signal really far, right? And you can hear it from quite a long distance. But you won't be able to send your data back. So this is one of the complaints we get from people all the time. Look, I'm looking at my phone or I'm looking at my laptop. Wi-Fi signal is 4 bars or 3 bars. It should be fine, and yet it's not working. Why isn't it working? And the answer is your phone or your laptop or whatever is reporting how strong the signal is it is hearing from your access point. It's not reporting how strong that signal is back at the access point that needs to hear what your phone or your device is transmitting. So that's what causes that problem where you say, hey, I've got a good signal, why is it not working? Chances are it's because you need to move closer because the access point or router that you're trying to connect to isn't able to pick up your signal. In addition, we've got to look at that signal to noise ratio as well. Your signal may be able to make it back, but there may be other sources of interference. So, you know, an example of this, you know, for an analogy is if you go into an empty conference room, you don't have to speak very loud or be very close to each other to hear each other, right? But now you fill up that meeting room with a bunch of other people and they're also all holding their conversations. You've now either got to get closer to each other or you've got to speak louder so you can be heard over the noise. That's the signal to noise ratio. You know, go to a crowded nightclub where there's music playing, you may have to be shouting at the top of your voice into each other's ears to be able to make out what each other are saying because the noise level is so much higher in that environment. So RF behavior here. So your signal goes out and it radiates out from where you're transmitting it from. So it behaves very similar to waves that you generate in a pond. So if you've ever been out to a pond, you've thrown a rock into the pond, you'll watch it create sort of a circular wave that then radiates out. And if you pay attention to those waves, a lot of times you'll see a lot of the same behavior. As the wave goes out, some of it's going to hit an obstruction here. And in the case of Wi-Fi, it may be able to pass through it, but it's going to be weakened and diffused as it goes through. Some of that wave is going to wrap around and go around the obstruction. If it hits a wall, it might bounce off of that wall and reflect back out. So the wave will hit and then come down here. And also as it hits various things, it can scatter and create little mini waves as it goes out. So the next thing I want to talk about here is basically what happens when it comes to transmitting. So when it comes to transmitting data, only one device can be transmitting at a time. So your access point transmits some data, then one of your client devices transmits some data, then a different client device transmits some data, and then the access point transmits some data, et cetera. So how does that work? Unfortunately, when it comes to Wi-Fi, when they were building Wi-Fi back in the early days of the 1990s, or I guess the later days of the 1990s, you know, there wasn't much volume. They weren't expecting streaming and things like that. It was just a way to transmit small packets of data. So because of the lack of volume that was there, they didn't want a lot of overhead. So they created just basically a very simple system. And that system is if your device wants to transmit, before it transmits anything, it stops and listens to see if anybody else is transmitting. If somebody else is transmitting, it uses a random number generator here to determine how long to wait. And then it checks again after that time has passed until it finds a window when no one else is transmitting. And then it will decide to transmit the data. So this causes some problems to us. So one of the first problems you run into is, you know, as you start adding more users, you know, I don't know what your homes are like, but in my home, I've got like 40 plus devices that are all connected to my Wi-Fi. So as you start adding more and more devices, it's more and more likely that two of those devices will decide to transmit at the same time. We'll see that no one else is currently transmitting and both will decide to transmit, which causes interference or a collision and causes that data to be lost. So that's a cause of loss as you add more and more users. The other thing you run into here is what we call the hidden known problem. You've got your access point here in the middle of the room. You've got a wireless user on one side and a wireless user on the other side. Both of these laptops are within range of the access point, so they can both communicate with it. However, they are not within range of each other. So when this device checks to see if anybody else is transmitting, it's not going to hear this device, and vice versa. So it's very common for both of these devices to not hear each other and decide to transmit at the same time. The access point can hear both, so it gets confused and the signals merge together and ends up with data being dropped. So this is what we call the hidden node problems. It's another issue, and also obviously as you start adding more and more devices onto the network, the more likely this is going to occur. So this is a big problem with Wi-Fi up until Wi-Fi 6. So Wi-Fi 6 does have some technology that solves this issue, and we'll talk a bit about it later. The other thing I want to talk about here is data rate versus throughput. And I'm using these terms in specific ways, and specifically sort of like how I most commonly see these terms used on Amazon and data sheets and customer reviews and things like that. And it's an area where people get a lot of confusion from. So in this term, what we're talking about here is data rate. So the data rate is going to be the measurement of how much data is sent from the radio on one device to the radio on another device. So you'll also see this often called a physical rate or a link rate. And this is how most Wi-Fi devices are marketed when it comes to speed. They're measuring the data sent between the maximum data sent between those two radios in ideal conditions. People, though, care about throughput. And the way most people are measuring throughput is using something like speedtest.net or Ookla or Google Speed Test, which is measuring data sent from your laptop's web browser to a server somewhere out on the internet and vice versa. So it's only measuring the data that is coming, being sent by the web browser or sent by the server. But what happens is when this data gets to your Wi-Fi device, it has to then have additional data added onto it, right? So in order to make Wi-Fi work in this RF environment where there's no regulation or minimal regulations, anybody can create a 2.4 or 5 gigahertz device, transmit data on it. So you get a lot of, interference issues, drop packet issues, you're transmitting through walls, your signal's bouncing off some of those walls, going through some of those walls. It causes some issues here. So because of that, there's a bunch of protocol overhead that goes on top of the data you're trying to send from your web browser as it gets transmitted from your computer to your access point before going out onto the internet. So that adds basically almost doubles the amount of data that you're seeing. So that's why what you'll see is you'll see like an N300 router, and people will complain they're only getting 120, 130, 140 megabits throughput when they're testing with something like speedtest.net, because it's not counting in the extra data that gets added on top of the data you intend to send to make Wi-Fi possible. It's also why if you look at something like Ethernet, the claimed speeds and the measurable speeds are very close because there's very little protocol overhead, because you're sending data over a fixed wire that basically has no other data on there, no other sources of interference other than what you are specifically putting onto that wire. So it doesn't need a lot of overhead to make it work. So that's why you see, the speeds that you see advertised, you won't see those speeds if you're doing something like speedtest.net or something like that. It used to be, and I think maybe still in Windows you can do this, but I know it used to be a lot of the Wi-Fi adapters had special software that you could see the actual current data rate. We'll also come back to this a little bit more and talk a little bit about some of the other things here which can slow your performance. So how do we increase speed? Now I'm looking at increasing speed from a technological standpoint. Not how do you do it in your home, but how does Zyxel as a manufacturer of this equipment, how do we make these products faster? So one of the ways of doing it is increasing the encoding with something called QAM. This is basically how much data we can cram onto a single frame that we're transmitting here. So 802.11n gave us 64 QAM. 802.11ac bumped us up to 256 QAM, and now with Wi-Fi 6, we're up to 1,024 QAM. That's possible. So a common question we get is, well, why didn't you do this earlier? Why did we have only 64 QAM versus 256? And because basically we need more and more horsepower, right, computing power to be able to take the data and basically compress it and encode it onto these radio waves So we need not only chips that have the power to do that, but chips that can do it efficiently, since so many Wi-Fi devices are battery based as you go, or mobile as you go around out there. The next thing to do is we increase spatial streams. We'll talk a little bit about that, but 11N started off as a 1x1. And then the other thing we can do is increase the amount of bandwidth we are using. So let's start talking a little bit about channels to put this in perspective. In the United States, we are allowed on the 2.4 gigahertz spectrum to use from channel 1 to channel 11. So that sounds great. There's another area where a lot of end users get confused. They go into the router interface and they see they've got 11 channels to choose from. So they say, hey, my neighbor's on 6, so I'll use 7 so we won't interfere with each other. But in reality, you are getting interference. So why? Basically, this 2.4 gigahertz spectrum is only about 60 megahertz total size that's available for you to use. And each of these channels that we're actually using is actually 20 megahertz wide, but the channels themselves are only spaced out approximately 5 megahertz. So what happens is you end up into a situation where you've only got 3 channels that can be used essentially before you start getting interference with each other. So channels 1, 6, and 11. Anything else that you use will cause interference to one or more other neighboring channels that somebody could be using. So that's one area where we get a little cause here. But so we've got 3, though, 20 megahertz channels that we can use. So one of the ways we talked about increasing speed was increasing the megahertz. So 802.11, and I believe it was added 40 megahertz channels as a way to get faster speeds, which is great. It works, but the problem is, remember, we've only got around 60 megahertz totally available here in the US between 1 and 11. And this is using 40, right? So you can't have 2. So as soon as you add a second device that's also operating at 40 megahertz, you're going to have overlap and you're going to have interference. And it doesn't matter necessarily if this is in your home or if it's in your neighbors, or if you're, especially if you're in an apartment or dorms or condos, you're going to be near other devices, other networks that are going to cause interference if everyone's trying to do 40 megahertz. So 40 megahertz lets us claim double speeds essentially. But in reality, you're not probably going to get that on the 2.4 channel because of just how little spectrum is there and how many devices are there. So that's why there was a big push in the early 11 or in the later 11N days, and then especially in 11AC, to move to 5 gigahertz channels. So you see here, we've got, I think it's around 26 non-overlapping 20 megahertz channels that everybody can use. So you can see, instead of 3, now you've got 26. So you've solved this issue, right, of interference between each other. So yes, that's true, but maybe not quite as much as we realize here. So you'll notice this middle section here is highlighted in orange. It says DFS channels. So basically what happened is the FCC said, hey, we're going to open up 5 gigahertz for unlicensed use. But the problem is we already have people using this spectrum, specifically most commonly radars. So whether it's weather radars or airport radars or military radars, radars are operating in this 5 gigahertz spectrum. So the FCC said you can use these channels as long as nobody else is using these channels for radar or some of these other government purposes. So in order to use these channels, you have to have special code in your access point or your client device that basically scans a channel before using it. I want to say it's a 30-second scan. I could be wrong, but I believe it's a 30-second scan before it can start transmitting any data. And if at any point it detects that, that suddenly there's radar being used, it then has to stop broadcasting and either wait for that to stop or switch to a different channel. And if that other channel is a DFS channel, it needs to make sure that no one's transmitting on for, again, I think it's 30 seconds before it starts transmitting. So that obviously causes some connection and quality issues. So a lot of people don't like that because they may get randomly thrown off their internet for 30 seconds while the AP finds a new channel to use if you happen to be within range of radar or government installation that uses these channels. Another problem you run into is to get DFS certification. It takes several months longer than getting standard Wi-Fi certification for the non-DFS channels. So for that reason, a lot of consumer equipment doesn't support DFS. So this is a common problem we run into with people saying, hey, I'm using your access points and you're not compatible with Bob's laptop downstairs. It won't connect to your access points. Something's wrong with your access point. And generally what happens is after we poke around, we find out they're using DFS channels, and Bob's laptop doesn't support DFS channels. Because in the rush to be the first to market with new consumer equipment, a lot of companies just bypass getting the DFS certification, since that will add several months lag to when they can launch the product. And because consumers aren't good about updating firmware or updating software on their stuff, so rather than release code later that adds it, they just don't bother because so many people won't. So this is a very common problem, especially on cheaper stuff like smart home devices, stuff that's just trying to be really budget. A lot of that doesn't support DFS, but we always get surprised by some of the laptops and tablets and things like that which don't support it. So that basically takes away these DFS channels in some cases, and if not, it's something that you have to keep in mind, that if you're using these channels, you may be running into some occasional disconnect issues, just depending on what's going on these DFS channels, what happens to be near you that isn't Wi-Fi based that uses them. So if you take away the DFS channels, you get something like 9 channels that are non-overlapping. So now we talked about increasing speed. That's how we came to this, right? So the way we increase speed, or one of the ways, is to increase the bandwidth. So we went from 20 megahertz to supporting 40 megahertz channels. So now we've only got 4 that can be used without going into these DFS channels. Then to increase speed more, we went up to 80 megahertz channels. So now we've only got 2 that can be used that aren't going to cause interference with each other. So now you're in an office environment where you've got, half dozen access points. Maybe you're in an office building, you've got a bunch of neighbors, they have some access points. So you're now in a situation where if you're trying to use 80 megahertz channels, you're much more likely to be interfering with each other and causing that to degrade your Wi-Fi performance. And now the big thing is 160 megahertz channels. So this is really big part of Wi-Fi 6. It's also supported by the Wave 211 AC devices. So that's how they get some of these faster speeds that you see claimed on the box or the data sheet. And you can see here, to use these 160 megahertz channels, there are no contiguous 160 megahertz blocks that don't use DFS. So now we'll move on to spatial streams. So we mentioned before, when the signal goes out, it hits objects, it can bounce and reflect off of them. So what happens is the signal causes something that we call multipath. Basically, the signal goes out and it follows these different paths, and these different paths are different lengths, right? This is the shortest path, a direct link from this device to this device, but the signal is also bouncing off of this desk and then coming over here. So it'll come in slightly later than the signal that came straight, and then you've got this other signal here that bounced off here. So this is something we call multipath. It can cause signals to cancel each other. It can also cause signals to combine. It can cause what's essentially an echo effect as the signals come in. So it was a bane of Wi-Fi in the early 802.11a, B, and G days. However, some smart engineers, some of which worked at a Zyxel subsidiary Zydas back in the day, came up with technology to take this and turn it into a positive. So this is how we get to MIMO, multiple in, multiple out. And basically what we're doing is we're sending different data streams on different antennas and relying on, and they're using the same frequency, so they're, in theory should interfere with each other. But because of the smart technology we've got in the chips now, we can take a listen and actually listen to the different echoes. So you'll have different antennas here transmitting different streams of data. In this case, it's 150 megabits on this antenna going out, 150 megabits on this antenna going out. And then on the client device, it has multiple antennas that can listen. And it'll use one antenna to listen to this signal and one antenna to listen to this signal because they're coming in at slightly different times due to the different distances that these beams travel. So we're calling each of these different signals here a spatial stream. So in this case here, in this illustration, we've got two spatial streams that we're using. So you send out two different streams of 150 megabits data, and it gets combined together for 300 megabits total. Another technology here you will see is called multi-user MIMO. It's using these spatial streams, same as before, sending different data on each spatial stream. But now, instead of being combined together into one faster spatial stream, you now get one 150 megabit spatial stream for this device and another 150 megabit spatial stream for this device. So your access point is able to send data to two different devices simultaneously. So when you're looking on the data sheets, you will see, especially on business class products, you will see the speeds. Instead of seeing AC 1900 or AC 2400 or whatever, you will just see 2x2, 3x3, etc. So that's telling you how many spatial streams are supported. It's just kind of assumed you'll know what the maximum data rate is for the particular technology built into the AP 11N versus 11AC. And it tells you what's going on. So if you see a 3x3, it tells you you've got 3 spatial streams that can transmit, 3 spatial streams that can receive. Now, if you look at consumer devices, especially laptops, phones, things like that, what you'll often see is these numbers don't match. So what you'll often see is something like, instead of a 3x3, you'll see something that says 2x1. So or actually more likely to be the other way around, 1x2. So that tells you you've got one antenna for transmitting, but you've got 2 antennas that are capable of receiving different streams. And then if you look particularly at Cisco access points, you'll see a number X number and then a colon and another number. So a really popular one is 4x4:3. So that tells you you've got 4 antennas that can transmit, 4 antennas that can receive, but only actually 3 of them can be used at any one time. So realistically, the difference between a 3x3 and a 4x4:3 is basically nothing in the real world. In theory, in some tough RF environments, maybe a little bit of a benefit, but not much. Give me just a second. Sorry about that. Let's get back into this. So now we'll put this all together, all the different ways we can increase speeds. So here we've got a column showing how many spatial streams are being used, what modulation type is being used, and how much bandwidth is being used. And then you combine them all together to get whatever your speed is. So in theory here, if we're looking at something with 3 spatial streams, 256 QAM, you can get up to 2600 megabits, right? So this is a very common, you'll see them on consumer routers advertising AC 2600. That's how they're getting that speed. But as we talked about, you probably, unless you're in a nice big home that's sort of on a large lot, you probably can't use 160 megahertz channels without causing interference, receiving interference from a neighbor who's trying to do the same thing. So you'll probably have to drop down to an 80 megahertz or 40 megahertz channel in order to maintain a good solid connection without interference. And that'll happen automatically. So instead of seeing the 2600, you may see a data rate of 1300 or 600. The other problem you run into here also is just there may be other sources of RF noise. You may be too far away. So as the signal gets weaker or the signal to noise ratio gets worse, it'll drop QAM. So you may drop from 600 megabits, it may drop down to 270 if it has to drop down to 16 QAM due to interference and things like that. And then maybe some of your devices don't support 3 spatial streams. Now you got to do that all again. So this is another reason why you may buy an AC 2600 product and you don't see those speeds, in addition to the protocol overhead that gets added on top of the data you're trying to transmit. You've also got to deal with your signal strength and your RF environment reducing the number of spatial streams, the modulation types, and the bandwidth that you actually can use at any particular time. Hope that makes sense. So this is another question we get all the time. How many devices can I fit on your access point? And the short answer to this is it really has almost nothing to do with the access point, unless it's something really old or really poorly made. It doesn't matter if you're buying a $75 access point or if you are buying a $600 access point. The number of users you can fit in there has very little to do with what the data sheet says. So, you may look at the data sheet, it may say 128 for this brand, 256 on this brand, 512 on this brand, but you're never realistically going to get to those numbers before the Wi-Fi itself starts limiting you. So basically, remember, we're all having to share airtime. Only one device gets to transmit at a time in most cases. So as you add more devices, you start running out of airtime for all of those devices to transmit data. And obviously the type of data they're trying to send also affects this. So if, you've got 60 users and all of them are just, checking their emails and browsing websites, it may work fine. But if they're all trying to stream Netflix, well, now you may only be able to get 10 or 20 on there before you start running into issues. Voice over IP over Wi-Fi is particularly sensitive to how many users you fit on there, even though they're using probably 56K or less bandwidth, because when you're doing voice, you don't have the ability to really buffer anything. So it becomes really important that packets are not dropped, that you don't run into jitter issues. So if you're trying to do voice over Wi-Fi, you may want to limit your access points to, 16 devices or something like that to maintain the call quality. So here's a sort of a simulation here for you. So we've got an access point that supports 3 spatial streams. In our thing here, everybody's got the same signal strength. Everyone's using a 5 gigahertz, 20 megahertz channel. So basically, if you've got laptops that also support 3 spatial streams, and each one of these devices is trying to do a 3 megabit data stream, you're going to be able to fit 34 devices on that access point before you start running into issues. And again, the issues aren't being caused by the access point. They're being caused by the Wi-Fi protocols and how much airtime is available and how fast you can send data during the available airtime. Same situation, but we use a device that only supports 2 spatial streams. We've gone now from 34 devices, you can only fit 21 devices on there, all using a 3 megabit, Netflix or YouTube stream. Why? Because you've lost out on a spatial stream. So you're not sending as much data at the same time as you could theoretically otherwise. So you reduces the overall capacity of how many users can be on there. Now you throw on a cheap Android phone here, you've only got 1 spatial stream. You can only fit 10 devices on that access point, still using the same 3 megabit stream. And this is just looking at spatial streams. It doesn't take into account some of the other stuff that would go in there, such as signal strength, encoding type, things like that, which may also degrade things. So it makes it really hard to say exactly how many devices you're going to get on your access point, because it just depends on what those devices are and what sort of data we need to be able to send. But as you can see here, just something like changing the spatial streams from 3 to 1 means the difference between 34 simultaneous 3 meg streams and 10 simultaneous streams being possible. So you're going to run into these types of issues long before you hit any sort of cap that's part of the actual access points specs. So we want to talk a little bit about co-channel interference and smart antennas. So let's see, how do we deal with this here? So we've talked about before, only 1 device gets to transmit at a time. Other devices using the same spectrum will either cancel out what you're doing or will raise the noise floor. So again, if you're using 2.4, in addition to your Wi-Fi radio, you've probably got some Bluetooth devices that are also using 2.4. You may have some proprietary devices using 2.4. Your microwave spits out 2.4. Your air conditioner may spit out interference on 2.4 or 5 gigahertz, etc. So this is co-channel interference, right? Other devices trying to use the same channel. That can also simply be other access points. If you got multiple access points in the area, whether it's in your office, your neighbor's offices, whatever, that's also, again, co-channel interference. So the way antennas work, right, traditional access points are designed to be mounted on the ceiling, and they send out a signal in what's essentially a circular pattern. We normally refer to this as umbrella coverage. So the ways you would deal with this in the past to prevent interference, so for instance, in this one here, we've got two APs, same channel, and you can see the signals overlap. So anybody that happens to be sitting here is going to experience interference issues. So the ways you would solve this in the past is you would, very carefully plot out where each of your access points are going, and then you would try to select channels. So you don't have no two APs next to each other using the same channel. But as we saw, with only 3 channels to choose from, oftentimes that's just not possible. The other issue you run into, as we talked about earlier, was this power output of your access points probably really strong and able to send that signal really far versus your phone or your tablet that's trying to connect to it and doesn't have a lot of power. So what happens is you would be surprised just how far away an access point can be and cause interference. Our lab guys are saying it can be up to over like 100 yards away and still be causing interference. So you would try to take care of those access points you manage by carefully plotting out the channels to use. And then the other thing you would do is you maybe turn down your power so the signal coverage goes out further so you don't have the interference here in the middle. The problem is, though, is you're lowering the signal strength of your access point, and that's going to lower your signal to noise ratio. So you may be trading off co-channel interference directly with just worse signal to noise ratio and end up with the same sort of speeds. So smart antenna is something that's been designed to solve this. We offer smart antenna on our higher end access points. Ruckus offers their version of smart antenna on most of their devices. And us two are pretty much the only guys that are really putting out smart antenna products. But basically, as we talked about before, your traditional access point has sort of an umbrella circular coverage area. And then if you're doing outdoor links and things like that, you may use a directional antenna to focus the beam. Smart antenna does something different. Smart antenna has the ability to use, instead of just one antenna pattern, hundreds of antenna patterns. So the smart antenna has an algorithm that basically in real time looks at where the client is that it's trying to communicate with, but it also looks at other sources of interference on the channel and tailors the antenna pattern to match both where the client device is, to focus its attention and the signal in that direction, but also to not listen to other sources of RF noise. And this is something that doesn't require any special software on the client side of things, doesn't require any special hardware. And it has the ability to work even with moving devices, something more like beamforming, which is a similar technology trying to achieve the same sort of thing. It doesn't really work too well on mobile devices. Smart antenna does. So we've got this example here that we did a test on. So this is a real world test. This is in a hotel. And this is using those small, low-powered access points that are designed to be one per room. So you can see here we're using 5 gigahertz, which also helps by not letting the signal go too far between the walls. And we've carefully plotted out the channels we're using to make sure we don't have any 2 APs directly next to each other on the same channel. Signal does go through the floor, and you can see here we're actually doing this on 2 different floors. So this is floor 1, floor 2. And we decided to do a test. So we took our product and we took a Ubiquiti product. Both us and the Ubiquiti have pretty much the same specs. The only real difference for Wi-Fi is the smart antenna versus no smart antenna. So when we had one access point operating on a channel, we did aggregated throughput here, and you can see Ubiquiti beat us out. Ubiquiti got 406 megabits per second. We got 404. Airtime efficiency was basically 67%. So of the theoretical 100% maximum usage of the channel we were on, we were using 67% of it. So now we do the same test again, and we do 2 access points. So we've got 2 access points using the same channel. And what you see here now is our aggregated throughput goes up to 785 megabits per second, where Ubiquiti goes up to 555. So a huge performance difference. So it goes from us being just slightly slower than Ubiquiti in a real world environment where we've got two different access points using the same channel, not next to each other, they're still spaced out, but close enough to cause co-channel interference. The smart antenna allows us to achieve much faster speeds. The other thing you'll notice here is the speeds are pretty much the same between access points, where in Ubiquiti, one access point is half the speed of the other. So the speed isn't evenly distributed over them. And you can see here with Ubiquiti, you get up to 95% of the theoretical 100% maximum airtime utilization. And we're able to get up to more than the max. We're able to get to 131% of the theoretical 100% maximum. How? Because with smart antenna, we're allowing devices that are connecting to two different access points to use the same channel simultaneously without interfering with each other. Because the smart antenna is basically able to choose an antenna pattern that ignores some of that interference. So now we do the same thing with three APs. Again, these three APs are not directly next to each other, but they are close enough that they are causing co-channel interference. And again, you see the same thing. Our aggregated throughput jumps up again. Now we're up to over 900 megabits aggregated throughput, where the Ubiquiti is basically the same at a maximum 554. Why? Because they're already basically at the maximum theoretical. In fact, with three of them, because of the inefficient ways Wi-Fi works to decide who gets to transmit, it actually gets worse as far as the theoretical airtime that they're using. So they're down to only 91%, where we went up from 130 something up to 155% of the theoretical maximum. And again, you'll notice the speeds are pretty evenly distributed between our access points, where with Ubiquiti without the smart antenna, it's really lopsided as to which ones get which airtime. So those are the benefits of smart antenna. So now let's talk a little bit about installing things. Generally, most access points, whether they're round or square, are designed to be mounted on a ceiling. As we talked before, they sort of have an umbrella-shaped coverage pattern. Oftentimes in the real world, though, you don't get to put these on the ceiling. You get stuck having to stick them on a wall somewhere for various reasons. So what happens is when you do that is the coverage pattern isn't optimized for how you're installing it. So a lot of that signal goes up into the ceiling, goes down into the floor. It can cause interference if you're on multi-floor buildings, as well as just getting not proper coverage in the area. So Zyxel does have a solution to this. If you don't want to pony up the money for smart antenna, several of our access points offer something that we call dual optimized antenna. So instead of having hundreds of antenna patterns, dual optimized antenna access points have two antenna patterns. One that's optimized for your traditional ceiling mount and one that's optimized for wall mount. And you can switch between those two based on where you install the hardware. It doesn't add a lot of cost to the price, unlike smart antenna. So just some general mounting tips. You want to mount the access point as central to the area you want to cover as possible. You want to mount it on the ceiling, and you want to mount it within reason as high as you can, because you want to create the shortest path possible between the client device and the access point, while also avoiding as many obstacles as you can. So by mounting it higher, you allow the signal to bypass cubicle walls, people walking around, laser printers, things like that, and just go through open air as much as possible to get to where the access point is. So one of the problems we get from people is, I can't mount it to the drop ceiling. The customer doesn't want me to drill holes in their drop ceiling to run the Ethernet through. They don't want me to mount the access point there. So what we've found is in the real world, you can simply lay the access point on top of the drop ceiling. The drop ceiling, most drop ceilings are just basically some sort of fiberboard. They don't absorb much of the RF signal. So placing an access point face down, just as if it was mounted on a ceiling, but on top of the drop ceiling allows you to have good centralized coverage without losing a lot of signal due to RF issues. Because the drop ceiling isn't absorbing much of the signal. So it's a good way to do it. It also makes your customer happy because they don't have to see the access point. You don't have to poke any holes in the ceiling to run the Ethernet cable through. So it is a good option for you. People also say, well, wait a minute, how about I just mount it on the ceiling above the drop ceiling? And generally the issue you run into that is the ceiling is also, you've got all sorts of metal ductwork. You've got the metal supports that are holding the drop ceiling, and all of those things will block or reflect RF signal. So generally not a good idea to mount it on the real ceiling above the drop ceiling because there's too many other obstructions that are causing issues. So in a hotel type environment, the traditional way of doing things here was to put one access point in the hallway, have it try to cover anywhere from 4 to 16 rooms, depending on construction and size and things like that. However, RF or Wi-Fi has gotten so much more demanding. When we started doing this in hotels, you know, it was generally one guy with his laptop trying to check emails. Now a person has multiple devices, right? They want to get their cell phone on the Wi-Fi so they don't have to use their data plan. They have a laptop. They may also have a tablet. They have kids. They have tablets. They have phones. So this sort of umbrella coverage pattern just doesn't work when you've got so many devices all trying to connect back to the same access point, especially when they're going through walls and plumbing fixtures and bathrooms and things like that. So the new trend in most mid-tier and higher hotels is one AP per room. And these are the same type of APs we were using in the previous smart antenna tests. Everybody has them now. And this is considered the best way now to do it, is you put one per room or one per every other room to provide coverage in those rooms. And that solves those issues and helps those loading issues. So you don't have as many devices per AP, crowding them up and eating up the Wi-Fi. Also, because a lot of these tablets and things are so low powered, they get a strong connection because they don't have to leave the room and go out down the hallway. They're connecting to an AP that's in the room for themselves. You want to look for locking options on the mounts. People will still access points if they can see them. So having a mounting mechanism that is difficult for someone to figure out how to release is always a good thing. It's also a good idea to turn off LEDs. So having an access point where you can disable the LEDs, because people don't want flashing green and orange lights shining down on them when they're trying to sleep. In public areas, the main thing to be looking at is user density. How many users are going to be in this area? And then add the appropriate number of access points based on the type of the users that are going to be there. Generally plan your coverage on a per area basis. So even if the restaurant is, sort of loosely connected to the lobby, you want to plan the lobby's Wi-Fi separately from the bar, from the restaurant, separate from the outdoor pool, etc. You want to use load balancing and client steering, limited to the area. So you want to make sure you're not, load balancing the entire hotel. You want to do it by floor or by coverage area. And generally, you want to use smart antenna-based products in any sort of environment where there's a lot of APs in the same area, or there's a lot of users in the same area. So, business rooms, conference centers, things like that really need smart antenna technology. It makes a huge difference. When it comes to schools, you need to ask some basic questions. How many students are in the room? Does each student have a Wi-Fi device? Is this a smart classroom where every student has a Chromebook or tablet that needs to be on Wi-Fi 24/7? Or is this a classroom where, kids only usually get on the Wi-Fi during free study periods or research periods and things like that? Is this teacher streaming stuff? So in a lot of modern classrooms now, the teacher, rather than, display something on a projector in the front of the room, will project videos and things like that directly to each student's tablet or laptop. So all of those things make a difference, right? So if your teacher is streaming video to 40 students, you need a different access point than if you've got 40 students and they only get on to browse the internet during free study periods and things like that. So that's some stuff to take into account. So both our wireless LAN controllers and our Nebula have a special algorithm that's specifically designed for classroom use to be able to handle the fact you may have 30 or 40 students all simultaneously connecting at the same time. So it helps with load balancing and things like that. But generally for class sizes of 20 students or more, go with 2 access points per room, not just one, especially if they're doing a lot of streaming or all the students are expected to be connected at the same time. If you've got 30 or more students, it really pays off to go up to something that's got smart antenna built in. So now let's talk a little bit about Wi-Fi 6, aka 802.11ax, aka high density Wi-Fi, and a bunch of other names. So the IEEE standard is 802.11ax. Wi-Fi Alliance is taking this opportunity to rebrand it Wi-Fi 6 and to retroactively rename 11AC as Wi-Fi 5, 11N as Wi-Fi 4, et cetera, et cetera, et cetera. So especially on consumer stuff, all the focus is going to be on Wi-Fi 6 as far as marketing goes. So the interesting thing with Wi-Fi 6 here to begin with is it works on both the 2.4 and the 5 gigahertz spectrum. Some people out there don't realize this, but if you're using an 11AC access point or router, the 11AC technology is only on the 5 gigahertz router. The 2.4 radio is still using 802.11n technology. So it was purposely built from the ground up as almost a rewrite of the 802.11 standard that's been designed to solve a lot of the problems we've been talking about today, specifically with interference issues between different access points and also larger numbers of active users connecting to the same access point. So these high density environments, whether we're talking density of APs or density of users, it's been designed to solve a lot of these issues as well as bump up speed. So the Wi-Fi Alliance, I need to fix that on the slide. Wi-Fi Alliance started certifying things, I want to say it was end of last year. But the interesting thing is the IEEE standard that Wi-Fi 6 is based off of still hasn't been finalized. I just checked here, and on August 27th, so what's that, a week and a half ago, they voted to create draft 7.0. So they're still working on the draft, and the draft still hasn't been approved. So final approval is now targeting Q1 of next year for official IEEE finalizing the standard. So the good news is at this point, though, even though we're still hashing out issues with drafts, the standard is far enough along that basically whatever the final version looks like, hardware or chipsets that are being shipped today should be upgradable to the full set. They're basically arguing over semantics and little things. Part of the problem that we run into, though, is that some of the earlier Wi-Fi 6, in quotation marks, products are not going to be able to support the full standard. So we'll talk about this here. I've got Qualcomm up here. So Qualcomm and Broadcom are the two biggest names when it comes to Wi-Fi 6 chipsets. They make the chips that go into all the different products. I've got Qualcomm up here, but Broadcom is essentially the same story as Qualcomm. So I don't need a second slide because it's basically the same thing with different names. But basically, a lot of the early Wi-Fi 6 chipsets that were shipped out there from guys like Cisco and Genius and things like that, especially on the consumer side of things, don't actually support a number of features that make Wi-Fi 6 Wi-Fi 6. So TWT, VSS color coding, these are big things to deal with interference between access points and allowing more users per access point before you start running into issues. So this cannot be upgraded via software or firmware to these early Gen 1 and Gen 1.1 and 1.2 chips. Same things with upstream OFDMA. Same thing with upstream MIMO, which allows multiple devices to send data to the access point at the same time, thereby allowing more devices on there. So this is really something to pay attention to. And it's not something that they make obvious, right? If you've launched a product that doesn't support all the Wi-Fi 6 features, they don't point that out. They don't say, hey, by the way, this doesn't support everything. No, they just call it Wi-Fi 6 and just don't mention any of these other features or functions. So in general, the Gen 2 chips from both Qualcomm and from Broadcom started to ship in quantity fall of last year. So one thing you can check is, has this product been around since before fall of last year? And if the answer to that is yes, you can be pretty safe to say it's not using a true Wi-Fi 6 chip. It's using this early draft that's missing important features. Another thing to look at, some vendors, Ubiquiti, for instance, their new Wi-Fi 6 access points, they didn't bother putting Wi-Fi 6 on both radios. They're still using a Wi-Fi 4 2.4 gigahertz radio on their new Wi-Fi 6 access points. And again, Wi-Fi 6 has been designed and is a huge major upgrade for 2.4, where interference issues are really, really big issue. Um, and Wi-Fi 6 helps solve a lot of those. But if you buy a Ubiquiti's new Wi-Fi 6 access point, you're not getting that technology on the 2.4 radio. So just to make clear here, as far as Zyxel is concerned, all of our Wi-Fi 6 products are using second-gen chipsets. All of them support all of the key features of Wi-Fi 6 and should be fully compatible with Wi-Fi or 802.11ax when it finally gets ratified. All of our stuff. So you don't have to worry about that. And all of our stuff puts Wi-Fi 6 on both the 2.4 and the 5 gigahertz radio. Another new technology you may have heard about is something called Wi-Fi 6E. So the FCC just, what was it, in July, I think it was, decided to take more spectrum that's currently in use and open it up for unlicensed use. So this is in the 6 gigahertz spectrum. So Wi-Fi 6 has been designed to work on any frequency, so you will see Wi-Fi 6 products that support 6 gigahertz spectrum. So this is where Wi-Fi 6E, the E is for extended or extension, to let you know that you can now support 6 gigahertz. So most of these devices will probably be 3 radio. You'll have 1 radio on 2.4, 1 radio on 5 gigahertz, and then a 3rd radio on 6 gigahertz. It's a huge amount of spectrum, 1200 megahertz. Remember, 2.4 is only 60 megahertz. So you're getting 7 new non-overlapping 160 megahertz channels. Part of the problem is, similar to the 5 gigahertz spectrum, is there are already people using this spectrum. Primarily news reporters. They use 6 gigahertz spectrum for live streaming audio and video for news reports and things. And utility companies use the 6 gigahertz spectrum to do smart meters and things like that. So they will continue to use those. So there's a new technology that has to be adopted called automatic frequency control, in order to be able to use these so you don't interfere with existing other users that have licensed 6 gigahertz devices. So as far as I know, this has only been approved in the US, but last I checked, EU was working on it. And the talk was before the end of the year, the EU should also open up 6 gigahertz. Wi-Fi Alliance is planning to start certifying devices in 2021. So this could be a potential game changer. All the benefits of Wi-Fi 6, plus a huge amount of new unlocked spectrum. The only major issue from my point of view that's maybe causing issues is we're in the 6 gigahertz spectrum. And again, as frequency goes up, the signal goes less distance because it's more easily absorbed or blocked. So, it remains to be seen what coverage is like, indoors into typical office environments, but it should be at least a little bit worse than current 5 gigahertz, if not a lot more worse. So we'll find out when it happens. It is something Zyxel is looking at for business stuff, but you'll probably see this first on consumer equipment, as is usual, just because business users generally want to invest in new technology. They wait for the price to come down and for all the bugs and kinks to be worked out, but it is something we're keeping an eye on. And you probably will see at least some other vendors coming out with business APs that use this space sooner rather than later. So that, guys, concludes today's webinar. Hope it wasn't too boring. Hope I didn't get lost too many times while talking about stuff. If you have any questions, send them in with the Q&A window. I will do my best to answer it. While we're waiting for people to type in questions, I just want to draw your attention to, we have a user forum these days. So go here to forum.zyxel.com. We've got a consumer forum and a business forum. And unlike some of the other forums that are out there from some of our other networking vendors, our R&D team and our product managers do keep an eye on that. So if you've got something that's maybe doesn't need an immediate fix, not only can you get help from your fellow users, there's a good chance if you post a problem, you will be able to get help and support from somebody in our team in Taiwan. In addition, it's a great place to post feedback, feature requests, things like that. We will see them. The people who make those decisions will be able to see those. And then you can always reach me offline. My email is Sean R. Sean is spelled SHAWNR at Zyxel.com, and I will be happy to respond to you offline and help you out that way as well. I am not seeing any questions. Oh, maybe someone said something by chat instead of Q&A. Let's check out chat. Alan asked about whether the session is recorded, and yes. So this will probably be posted to our YouTube, Zyxel Channel America, probably within the next 24 to 48 hours. In addition, I have done this webinar before, so all the previous versions of this webinar should also be on our YouTube channel. Be careful when you're poking around the YouTube channel. The split our channel. We used to have one Zyxel channel, now we've got two. A lot of these webinars used to be on the old channel, so then when they migrated them over to the new channel, it put the older presentations before the newer ones. So just keep an eye on that. Pay attention to what the date is. It says I had somebody who missed the last time we did this webinar, and they went to watch it, and they said, "Hey, Sean, your stuff's really out of date," and it was because they were looking at one from October of the year before. So pay attention to the date, but this should be up there in 24 to 48 hours. Brent says he did have some questions, but he can't remember them now. So Brent, just take a note of my email. Feel free to reach out to me directly, and I'll be happy to answer the questions as best I can. But I'm not seeing any other questions, so I'm going to go ahead and end today's webinar. Thank you for joining us, guys. I've got a dedicated Wi-Fi 6 webinar coming up. I think it's next week or the week after, where I'll be talking about, our 5 business class Wi-Fi 6 models, a little bit more in-depth on some of the features and benefits of Wi-Fi 6. I know Tri's got a number of webinars also this month for like our security and switch products, so think about joining those. And as always, feel free to email us your ideas for what you would like to see us presenting on. We want these to be valuable for you. You're taking 30 minutes to an hour of your time, so we want to make sure you're getting what you want. So let us know if we're letting you down with what we've got, or if you have ideas for other topics you would like to see us cover in the future. We are also, I believe, either just rolled it out or in the process of rolling out an online training system with quizzes and things like that, as well as pre-recorded presentations going through things, training you on them. So if that's not published yet, it should be being published here any day now. So thanks for joining us, guys. And again, feel free to email me with any questions you may have.